In this video, we are going to talk about the dual space and the dual map. This is our overview slide, which we'll spend about 5 minutes or so on before going over each of these topics in more detail and with more examples. We start by defining the linear functional on a vector space V. So the linear functional, well, they're linear maps or functions from V to F. So they're linear, they're functions, hence linear functional. So a linear functional is an element of the space of linear maps from a vector space V to a field F. So the field F could be the real numbers, it could be the field of complex numbers. One of our first examples in your book, and your book denotes these linear functionals with these phis, is the function that maps the space of polynomials over real numbers onto the field of real numbers. So phi takes a polynomial p and it maps it to 3 times the second derivative of p evaluated at 5 plus 7 times p evaluated at 4. And you'll see that this produces a single real number, a scalar. So phi is a linear functional on the space of polynomials over R. Our second example will be p goes from the space of polynomials over R to the field of real numbers. Phi of p is equal to the integral from 0 to 1, our function p of x dx. So here again, phi is a linear functional. It's a function, and it produces a scalar r. Once we have defined these linear functionals, again, they're functions that are linear that maps to a field, to maps to scalars. We can define the dual space of V. So given a vector space V, we can denote the dual space as V prime, and that's the vector space. So the dual space is a vector space of all linear functionals on V. So in other words, V prime, the dual space, is the set of all linear functions from V to some field F. And looking back at our example, the first one, phi of p, which takes our polynomial and then maps that to 3 times the second derivative of the polynomial evaluated at 5 plus 7 times the polynomial evaluated at 4, and this other linear functional that takes a polynomial and maps it to 0, the integral 0 to 1 p of x dx, these two functions, this phi of p and this phi of p, are vectors in the dual space. So we have our original vector space, which is the space of polynomials over real numbers. We have this then dual space, p of r prime, which is equal to the set of functions. These are two examples, but we're looking at all the functions now, from p of r to f. Next, we have this theorem that tells us if V is finite dimensional, then the dimension of the dual space is equal to the dimension of V. And the surprising result is that V and its dual space are isomorphic. Now that we know that the dual space is a vector space and it's isomorphic to V, we can define the dual basis. So if we're given V1, V2 up to Vn as a basis of V, then the dual basis is the list phi1, phi2, phi3. Remember, these are functions now of the elements of the dual basis, where each phi sub j is the linear functional on V such that phi of j, when you operate on the kth basis vector of V, is equal to 1 if k equals j, and 0 if k does not equal to j. So in other words, the phi sub j from the dual basis will pick out the jth coordinate of our vector. And we have this theorem that formally says the dual basis is a basis of the dual space. So suppose V is finite dimensional, then the dual basis that we discussed over here is the basis for V prime. Next, we'll talk about the dual map. Now, if T is a linear map from vector space V to W, then the dual map of T, which we'll denote with this T bar or T prime, in the space of linear maps from W prime to V prime, is defined by T bar of phi is equal to phi composed of T for phi in W prime. I find this picture helps explain the idea of the dual map. So T is a map, a linear map from V to W. So here I have my vector space V and my vector space W, and T maps from V to W. It'll take vectors in V, map it to W. The other thing is that we have these dual spaces for V and W. So just looking at the dual space of W, those are the functions. It's a set of functions, phi, that map from W to a scalar field F. So here I have W, it maps to these scalars. So maybe it's real numbers, maybe they're complex scalar numbers. What this dual map does is it says once I have some function in W bar, in other words, some function that maps from the space W to the scalars F, I can then create a function, right? This linear map will give me back a function in V bar, in other words, that goes from V to the scalar fields F. And the way I'm going to do that is I'm going to take this phi and I'm going to compose it with T. So remember, our dual map then takes phi, and remember phi maps from W to F, and I'm going to compose it with T. So remember, when we do function composition, the order of the functions we execute is we go from inside out. So our new resulting function is this phi composed of T. So if we take now a vector V from our vector space V, first we operate with T and we move over to W, and then from W we take this phi and we move to the scalars. So now this function composition has created a mapping that goes from V to F, and that's what the dual map is about. We'll list out some algebraic properties of dual maps, and then we'll talk about null space and range of the dual linear map. First, we introduce the annihilator, which is very analogous to a null space. So for U, a subset of V, the annihilator of U, denoted with this U of 0, is defined as the functions in the dual space such that phi of U is equal to 0 for all U in the subset U. And we have this theorem, the annihilator itself is a subspace, just like the null set space is a subspace. So suppose U is a subset of V, then the annihilator is a subspace of the dual space. And we have the theorem, the dimension of the annihilator, suppose V is finite dimensional and U is a subspace of V, then dimension of U plus dimension of the annihilator equals the dimension of V. This is totally analogous to the null space and range of a linear map, except now we're in particular talking about our functions in the dual space. We'll look at the null space of the dual map T bar. Suppose V and W are finite dimensional and T is in the set of linear maps from V to W. Then 1, the null space of the dual map is equal to the range of the annihilator. 2, dimension of the null space of the dual map is equal to the dimension of the null of T plus dimension of W minus dimension of V. We have these next two theorems. T is surjective is equivalent to the dual map being injective, and T is injective is equivalent to T, the dual map, being surjective. Finally, we'll look at the matrix representing the dual map, and we will see that it is the transpose of the matrix representing the transformation T. And that wraps up our overview. So we're ready to go back and take a closer look at everything, and we'll start with the linear functional. A linear functional on a vector space V is a linear map from the vector space V to a scalar field F. In other words, a linear functional is in the set of linear maps from V to F. It is linear and it is a function, and therefore it's a linear functional. Our first example is this linear functional phi, and our linear functional in your book will be denoted with a phi, and it'll take a vector in R3 and map it to the field of real numbers. And it's defined as phi of our xyz, our vector in R3, is equal to 4x minus 5y plus 2z. Now you can see we have mapped from R3 to a real number. Once you have a value for x, y, and z, like 1, 2, 3, that's equal to the real number 4 times 1 minus 5 times 2 plus 2 times 3. So therefore, our phi is a linear functional on R3. Technically, I should also prove that phi is indeed a linear map, but linear maps was a topic from a previous video, so I'm going to suggest either you review that or I will assume that you know how to prove that phi is linear for all the following examples. Our next example starts with a set of fixed constants C1, C2 up to Cn. In other words, it's a vector and f of n. Now our first linear function will map from f of n to f, and we're going to define it by, we take our vector from fn, which is x1, x2 up to xn, and we're going to map it to the scalar c1x plus c2x2 plus up to cnxn. So in other words, we make a linear combination using our scalars and our coordinates. And we see that phi goes from f of n, our x1, x2 up to xn, and it maps to our real number here, the linear combination. Example 3 is the linear functional that goes from the vector space of polynomials over real numbers to real numbers. So phi will take a polynomial p, it'll map it to 3 times p double prime evaluated at 5 plus 7 times p evaluated at 4. We see that phi is a linear functional on p of r. It takes a polynomial and then it gives us a real number. For example, if our polynomial p1 of x is equal to 2x squared plus 3x plus 1, then we see our second derivative is equal to 4x plus 3, and the second derivative is equal to 4. So phi of our 2x squared plus 3x plus 1 is equal to 3 times p double prime evaluated at 5, which is just equal to 4, plus 7 times p evaluated at 4. That's 7 times, where's p evaluated at 4? 2 times 4 squared plus 3 times 4 plus 1, which is equal to 215 if I did my addition and multiplication correctly. If our polynomial is equal to p2 is equal to x cubed plus 3x squared plus 5, we see that our first derivative of p2 is equal to 3x squared plus 4x, and our second derivative will be equal to 6x plus 4. So when we plug our polynomial into phi, so phi of x cubed plus 2x squared plus 5, we're going to get that's equal to, where's our phi definition? 3 times the second derivative evaluated at 5, so that's 3 times, here's our second derivative evaluated at 5 is 6 times 5 plus 4, and then our phi is 7 times p evaluated at 4, so 7 times p evaluated at 4 is 4 cubed plus 2, 4 squared plus 5. And if I did all my addition and multiplication correctly, that will be equal to 809. And you can see again, this is how our phi then takes a polynomial and maps it to a real number. Our next phi maps from the same space of polynomials over R to R, but we're going to define this phi as being the mapping that goes from the polynomial to the scalar that we get when we integrate our polynomial and then evaluate between 0 and 1. We see that phi then takes a polynomial. It maps to the real numbers because once we plug in 0 and 1 to the antiderivative, we will get a real number. And so we are mapping to the real numbers, so phi is a linear functional on p of r. I'm going to repeat my examples from the previous number 3 problem or example. So phi p of 1, I'm going to let p of 1 still equal to 2x squared plus 3x plus 1, but I'm going to plug it into this new phi. So that's going to be the integral from 0 to 1, 2x squared plus 3x plus 1. So I get 2/3 x cubed plus 3/2 x squared plus x evaluated at 0 and 1. So when you plug in 1, you get 2/3 plus 3/2 plus 1 minus 0 plus 0 plus 0. So this is our final answer, but I didn't bother to add the fraction. But you can definitely see it's a real number. Now, if we take p2 from over here and plug it into this new phi, we get the integral from 0 to 1 of x cubed plus 2x squared plus 5. And when we do our integral, evaluate between 0 and 1, we get the real number 5 and 11/12. Now that we know what linear functionals are, we can define the dual space of a vector space V. So given a vector space V, we can define the dual space and denote it with this V prime or V bar is the vector space of all linear functionals on V. That is, our V prime is equal to the set of linear maps from V to F. So considering our last two examples, this one here where phi went from the space of polynomials to the real numbers, and it was defined as phi would take a polynomial and map it to 3 times the second derivative evaluated at 5 plus 7 times the polynomial evaluated at 4. And we took this other phi that maps from the space of polynomials to the real numbers. We defined that as taking the polynomial and mapping it to the real number that we get when we integrate from 0 to 1 p of x dx. These are both from the same space, p of r, and then they both map to r. And therefore, these two functions, these two different functions, the one with the derivatives and the one with the integral, they are both vectors in the dual space. P of r prime is equal to the set of linear maps from P of r to F. I shrank our previous examples down a little more to give me space for this drawing. So here is my first phi of P. That's the one that takes a polynomial and maps it to 3 times the second derivative evaluated at 5 plus 7 times the polynomial evaluated at 4. That's this example here. And again, we said it maps from the space of polynomials to R. It took this polynomial 2x cubed plus 3x plus 1 and mapped it to the real number 215. It took the second polynomial x cubed plus 2x squared plus 5 and mapped it to the real number 80. I think that's a 4. Maybe it's a 9. So let's just pretend like it's a 4 here. Maybe I got my math wrong or copied it wrong. This is my first phi, my first mapping from the space of polynomials to R. I have another mapping, that was our next example, from the space of polynomials to R, which was the integral definition. So it took the 2x squared plus 3x to 3 1/6, and the x cubed plus 2x squared plus 5 to 5 11/12. I could kind of come up with another phi that takes polynomials to real numbers, and then there's going to be an infinite number of these, well, possibly an infinite number of these. So this whole set of mappings then is my dual space. That's my V prime. This next theorem is important because of the implication, which we'll discuss in the next slide, but that's that the dimension of the dual space is equal to the dimension of the original vector space. The proof is fairly straightforward. And this proof is straightforward from this theorem here that we had discussed in a previous video about isomorphisms. It says that the dimension of the set of linear maps from V to W is equal to the dimension of V times the dimension of W. So we're going to apply this theorem now to our set of linear maps from V to F. That is our dual space. And what we will get then is dimension of V prime is equal dimension of our space of linear maps V to F, which is equal dimension of V times dimension of F. Now, since F is a scalar field, its dimension is 1, so this becomes dimension of V, and therefore we have shown dimension of V prime, or the dual space, is equal to the dimension of V. And the significance of this theorem is the result is that the vector space V and its dual space are isomorphic, and that comes from this theorem here. Also from our video about isomorphism, is dimension shows whether vector spaces are isomorphic. That is, two finite dimensional vector spaces over F are isomorphic if and only if they have the same dimension. And remember, an isomorphism means same shape. So an isomorphism is essentially a relabeling of vectors in V to our vector TV in W. In other words, in our previous example, we were looking at V being the space of polynomials over R, then all these mappings, the set of all the mappings, there's a isomorphism between the space of polynomials over R and the set of mappings from the polynomials to the real numbers. We have a new vector space now, the dual space of V, and we need to find its bases. And what we are going to do is we're going to start with the bases v1, v2, up to vn of the vector space V. Then the dual basis of v1, v2, vn is going to be the list of functions v1, v2, v3, up to vn, all elements of the dual space of V, where each v sub j is the linear functional on V such that v sub j operating on the kth basis vector of V is equal to 1 if k equals j, and 0 if k does not equal to j. And just note, we're defining v sub j only in terms of the bases of V, because remember, once we know how a function or a transformation operates on a basis, we know how it operates on all vectors in V, since every vector in V can be written as a linear combination of the basis vectors. We will do an example. What is the dual basis of the standard basis for F3? Since we define our dual bases in terms of a basis for V, the first thing we want to do is note the standard basis for V. In this case, V is equal to F3. So our basis for F3, or the standard basis for F3, is equal to the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, or E1, E2, E3. We are ready to define our dual bases now, and remember, it's the same dimension as V, so we're going to have a phi1, a phi2, and a phi3. These are three different functions, and the key thing is that our function is equal to 1 when j, the index of our phi, is equal to the index of our basis vector for V. So in other words, our phi sub 1 is going to operate first on our first basis vector, and it's going to give us 1, because in this case our 1 corresponds to matches our basis number. This is our first basis vector, this will be 1. But when we operate phi of 1 on our second basis vector, since this index is 1 and this index is 2, that'll be equal to 0. Similarly for this, since phi of 1, the index is 1, and this index is the third basis vector, the indices don't match, so it'll be equal to 0. And I have phi 2, phi 3, and again, we're using this definition here. Our phi of j is equal to 1 if j equals k, and it's 0 if k and j are not equal. So you can see here, phi of 2 is equal to 1 when we put our second basis vector in, 0 elsewhere, and phi of 3 is equal to 1 when we put our third basis vector in, 0 elsewhere. I'm going to use this example now to explore this formula here. So what this formula is saying, if we have any functional in the dual space of F3, then we can write that functional as a linear combination of the bases for the dual space, which is A1 times phi1, the first basis vector, plus A2 times second basis vector phi2, plus A3 times phi3. To solve now for our constant coefficients A1, A2, and A3, I'm going to start by choosing the vector v1, that is the first basis vector. In this case, the first basis vector would be 1, 0, 0. But in general, I'm just going to choose the first basis vector, and I'm going to plug it into phi. So I have phi v1 is equal to a1 phi1 v1, a2 phi2 v2, plus a3 phi3 v3. And now we know that this phi1 v1, this is equal to 1. It goes to 1 because remember, here phi1 picks out the first basis vector. Over here, we have phi2 v1, that goes to 0, and phi3 v1 also goes to 0. Again, because our phi1 on our second and third basis vector will go to 0. Similarly, we can set v equal to v2, and we'll find that phi of v2 is equal to a2, and when we set v equal to v3, then phi of v3 is equal to a3. So finally what we get is our phi is equal to phi of v1, phi1, plus phi of v2, phi2, plus phi of v3, phi3. So remember, this phi is a random functional in our dual space. Our phi of v1, this is our random functional evaluated at v1, and this phi1 is our first basis vector for the space. This phi2 of v2, again, that's our functional evaluated at v2 times the second basis vector of the dual space, and then phi of v3 is our random functional evaluated at v3 times the third basis vector of our dual space. To look at this formula, I'm going to do this example. Let our vector space equal to R2 with the bases 2, 1, and 3, 1. We want to find the dual bases for this space R2. We will start with our first basis vector phi1, and we'll make phi1 pick out our first basis vector of R2. In other words, phi1 of 2, 1 will equal to 1, whereas phi1 of 3, 1 will equal to 0. If we want to evaluate phi1 at some arbitrary vector in R2, x, y, then we're going to have phi1 times x times the basis vector 1, 0 plus y times the basis vector 0, 1. Since our linear functional is linear, we can rewrite this as our scalar x times phi1, 1, 0 plus y times phi1, 0, 1. This was an easy decomposition, but we don't have our bases in terms of 1, 0, 0, 1. We don't have the standard bases. We have this bases here, 2, 1, and 3, 1. So we need to write our 2, 1 in terms of our standard bases so we can convert this over to phi of something of our standard bases. So our 2, 1 is equal to 2 times 1, 0 plus 1 times 0, 1. So now we can write our phi of 2, 1. Again, because it's linear, we can take out our scalar 2 times phi of 1, 0 plus 1 times phi of 0, 1. And this phi of 2, 1, we have that equal to 1. Similarly, for phi of 3, 1, we're going to write 3, 1 as a linear combination of our 1, 0, 0, 1. And then phi 1 of 3, 1 then becomes 3 times phi 1 of 1, 0 plus 1 times phi 1 of 0, 1. And from our bases, this is going to be equal to 0. And now we have a system of equations where our variables are phi 1 of 1, 0 and phi 1 of 0, 1. This is our solution, and these here are our coefficients to our unknowns. So in other words, again, phi 1, 1, 0 is our first unknown, phi 1, 0, 1 is our second unknown. These are our coefficients, 2, 1, 3, 1. I got them from here, and they equal to 1, 0. This is our matrix equation. I'm going to use our regular row-reduced echelon form. So I'm going to use our augmented matrix, 2, 1, 3, 1, augmented with our solution vector here. So 2, 1, 3, 1 augmented with 1, 0. I row-reduce this, which gives us the equation now that our first phi 1, 1, 0 will be equal to negative 1 here. And our second variable, phi 1, 0, 1, will be equal to our 3. Now I'm going to rewrite this equation here, but instead of using these column vectors, I'm going to have row vectors. So I have my phi 1 xy, that's what this is, phi 1 xy, is equal to x times phi 1, 1, 0, x times phi 1, 1, 0, plus y times phi 1, 0, 1. Here I have just solved for phi 1, 0, 1 is equal to negative 1, so I have x times negative 1. Phi 1, 1, 0, 1 is equal to 3, so I have y times 3, which means my phi 1, my first basis vector, is equal to minus x plus 3y. This is the function that maps from R2 to R. I can do the same analysis for phi 2, where I'm going to have phi 2, it's going to pick out our second basis vector. So phi 2 of the first basis vector, 2, 1, will equal to 0, whereas phi 2 of our second basis vector, 3, 1, will equal to 1. When I put it into my system of equations, I'm going to find that phi2 of 1, 0 is equal to 1, and phi2 of 0, 1 will equal to negative 2, which means phi2 of xy is equal to 1 times x minus 2 times y. So these are my two functions that are our bases for my dual space. That is, my dual basis now is going to be minus x plus 3y, x minus 2y. I shrunk this down to give me more space, but the last thing we concluded was the dual bases for this space is equal to minus x plus 3y, x minus 2y, which means any functional in the dual space, again, v in this case is equal to R2, so any functional, anything that converts vectors from R2 to a real number can be written as a linear combination of these two bases vectors. This is phi1, this is our bases vector phi2. And we had previously, just a few slides ago, had calculated the coefficients are going to be our phi, our functional, evaluated at v1, that is the bases vector for v, in this case R2, R2, 1, plus phi of v2, again, this is our functional evaluated at our second basis vector, times phi2, our second basis vector for the dual space. And one other thing I want to mention about this example, you can kind of do a sanity check here, or you can absolutely do a sanity check here. Remember, our phi of 2, 1 needs to equal to 1. Well, you can plug it in. Our phi1, our first basis vector, is negative x plus 3y. So when x is equal to 2, we have minus 2. When y is equal to 1, we have plus 3 is equal to 1, which is exactly what we want. But we also want phi1 of our second basis vector, 3, 1, to equal to 0. So when we plug in 3, 1 in here, we get minus 3 plus 1 times 3 is 3. We get 0. And then for our second basis vector, phi2, evaluated at 2, 1, that should give us 0. So when we plug this into our second basis vector, we have a 2. X is equal to 2. Minus 2 times y, that's minus 2 times 1. So we get 0. And phi2 at 3, 1, our second basis vector, is equal to our 3 minus 2 times 1, which is equal to 1. So this here agrees, or this dual basis will give us the right numbers for our phi1 and our phi2. Our next example, what is the dual basis of the standard basis for polynomials of degree 2 or less? So our standard basis for polynomials of degree 2 or less is equal to 1, x, and x squared. So phi1 then is going to equal to 1 when we put in our first basis vector, and 0 when we put in the second and third basis vector, x and x squared. Phi2, on the other hand, is equal to 1 when we put in our second basis vector, but 0 when we put in our first and third, and phi3 is equal to 1 when we put in our third basis vector, and 0 when we put in our first and second basis vectors. This work we've done to find the dual bases is formally stated in this theorem. The dual bases, this basis here we just defined, is a basis of the dual space. So suppose V is finite dimensional, then the dual basis of a basis V is a basis for the dual space. And we will not be proving this theorem. I believe it is proved in your textbook. Our next big topic is the dual map. So if T is an element of the set of linear maps from V to W, then the dual map of T is the linear map, we'll denote it with T prime, is in the space from W prime to V prime, defined by T prime of phi is equal to phi composed of T for phi in W prime. I find a picture really helpful in understanding what's going on here. So let's start by reading the definition again. If T is an element of the set of linear maps from V to W. So let's start with the drawing. Our set V, our set W, and T is a map that goes from V to W. And that's this first part here. We get to defining next the dual map of T. We'll name that T prime, and that is in the set of linear maps from the dual space of W to the dual space of V. Remember, the dual space is the set of linear functionals from V to F. So the dual space of W is the set of linear functionals from W to F. Here I represent this with phi going from W to F. So this is part of the dual space of this W prime. We also have this V prime. Those are going to be linear functionals from V to F. But what this map T bar is going to do for us, it's going to let us create a map from V to F using this map we have from W to F. And here's the function, the dual map, that takes a function from the dual space of W and gives us a function in the dual space of V. So it takes this phi and it composes it with our original linear function from V to W. So now we can take a vector in V and map it to F using this function composition. Remember, function composition kind of goes from the inside out. So if we have phi composed of T of V, first we let T operate on V and we get mapped to W. And next, once we have a vector in W, we let phi map on W to give us a scalar. And this function composition then gives us a mapping from V to the scalar. In other words, it gives us a mapping to the dual space of V. I have this summarized here. Now the dual map of T composes maps T and phi to get a map from the vector space V to the scalar field F. And our new function that we get with this function composition is now part of our dual space of V. So again, our dual map is in the space of functions that go from the dual space of W to the dual space of V. Remember, our dual map takes a map and it gives us a new map. It takes a map from the dual space of W to the dual space of V. Now's a good time for some examples. I have our definition of the dual map here as well as our drawing for your reference. And for our transformation from V to W, we're going to use D as our transformation to go from the space of polynomials to the space of polynomials. We'll define D as taking a polynomial and then mapping it to its derivative. So D goes from some polynomial to its derivative, also a polynomial. For our first example of this dual map, we're going to take our phi of P. That is, it's going from W, this set of polynomials, into our scalar field F. So D phi of P is going to be equal to P evaluated at 3. So now we want to find the dual map for phi. It's kind of funny now because this prime here denotes our dual map, whereas this prime here denotes derivative. But anyway, we want the dual map of phi. And to do that, we're going to compose phi with T. In other words, we're going to compose phi, which we've defined here, with D, which we defined as the derivative. So if we take a polynomial, the first thing we are going to do is take its derivative. So we get phi of P prime. And now phi is just the polynomial evaluated at 3. So that's going to be P prime evaluated at 3. And I've drawn this picture here. Again, our original mapping, our transformation, goes from the space of polynomials to the space of polynomials, PR to PR. And our derivative function then maps from our space of polynomials to our space of polynomials. Next, we took phi, which maps from W to our scalar field. And in this case, phi is equal to P of 3. So finally, our dual map then will take this function, phi, and create a new function, phi composed of D. So when we plug in a polynomial, we get P prime of 3. But what we have is, again, this function phi And our dual map then defines a function from our vector space V, in this case P of R, to F, and it defines this function. I mean, you can kind of think of it as this function here, except that it does this in a roundabout way by first going through our transformation to go from PR to PR, and then our transformation to go from the space of polynomials to the scalars. We can do the same thing with our integral example. In other words, we can go from our space of polynomials to F by doing this integral function, integrating P, and then evaluating at 0 and 1. So then to find the dual map of this phi, so to find the dual map now using this phi, and again, we're still using the same transformation D, which is the derivative, we're going to compose phi with the derivative. So in other words, it's going to be phi, the derivative of p. So phi of p prime, which is the integral 0 to 1 of p prime, which is simply equal to p evaluated at 1 and 0, which is p of 1 minus p of 0. Next, we have some algebraic properties of dual maps. So the dual of s plus t is equal to the dual of s plus the dual of t. The dual of a scalar a times t is equal to a times the dual of t. And then last, the dual of s times t is equal to the dual of t times the dual of s. This looks a lot like a complement or transpose of matrices, and the order of the matrices is reversed. Next, we'll look at null space and range of the dual linear map, and we'll start with the annihilator. For U, a subset of V, the annihilator of U denoted with this U superscript 0 is defined by phi in the dual space such that phi of U is equal to 0 for all vectors U in the subspace U. For our first example of the annihilator, let U be the subspace of the polynomial over R consisting of polynomial multiples of x squared. Let phi be the linear function on P of R be defined by phi of the polynomial is equal to the polynomial's derivative evaluated at 0. Is phi in the annihilator of U? We start by noting that U looks like the polynomials that are scalar multiples of x squared, so a is a scalar. We can then take phi of our polynomial. Our phi is equal to the first derivative evaluated at 0. So our first derivative of ax squared is 2ax, evaluated at 0 at x equals 0 is equal to 0. Since this ax squared represents the whole subspace of U, that means phi takes all vectors in U, the subspace U, to 0. That puts phi in the annihilator of U. In particular, phi is one of the functionals that map all of the polynomials of the form px equals ax squared to 0. So there may be other functionals as well, so phi may not be the entirety of the annihilator, but it is one of the functionals in the annihilator. Our next annihilator example, let E1, E2, E3, E4, E5 denote the standard basis of R5, and Phi1, Phi2, Phi3, Phi4, Phi5 denote the dual basis of R5. Suppose U is equal to the span of E1, E2, in other words, vectors where we have a first and a second coordinate and the 0 for the third, fourth, and fifth coordinate. Show that the annihilator of U is equal to the span of Phi3, Phi4, and Phi5. To show this equality between our annihilator and the span of Phi3, Phi4, Phi5, we're going to take the standard tactic of showing equality of two sets, which is to show that the first set is a subset of the second set, and also the second set is a subset of the first set. Hence, the two sets must be equal. We will start with the first containment proof that our annihilator of U is contained in the span of Phi3, Phi4, Phi5, this here. We're going to start by letting phi be in the annihilator of U. Since Phi1, Phi2, Phi3, Phi4, Phi5 is a dual basis over here, we had designated that as our dual bases, then our phi can be written as a linear combination of our dual bases vectors. Our phi of E1 then, we write phi as a linear combination of our bases vectors of E1. And now remember here, our E1 is going to pick out our first coordinate, C1. But also, since E1 is in U, because here we said that U is the span of E1 and E2, and we also have that phi is in the annihilator from our assumption here, the first assumption, that means phi of E1 has to go to 0, which means here C1 must be equal to 0. Similarly, we can show that phi of E2 is equal to C2, which will be equal to 0, which means that our phi over here, now with C1 and C2 equal to 0, is in the span of C3, C4, and C5. So we have that written here, and this is the containment we wanted to show. To prove the second part for our equality, we need to show that the span of phi3, phi4, phi5 is a subset of the annihilator of U. So we're going to start by letting phi be in the span of phi3, phi4, phi5, which means phi is a linear combination of phi3, phi4, phi5. Now when we consider a vector U in our subspace U, our vector U is of the form x1, x2, 0, 0, 0. So I've written that here. Now if we want to take our phi of U, that's phi of x1, x2, 0, 0, 0, our phi breaks down into C3, phi3 plus C4, phi4 plus C5, phi5 of x1, x2, 0, 0, 0. But you can see here, these are going to pick out the third, fourth, and fifth coordinates. Those are just zeros, which means our final answer is 0. And since phi of U now, for any U of this form, which is exactly our subspace of U, is equal to 0, that puts phi into the annihilator of U. And now we have proven both of these statements that the annihilator of U is a subset of the span of phi3, phi4, phi5, and the span of phi3, phi4, phi5 is a subset of the annihilator of U. Therefore, the two sets must be equal. We have a theorem about the dimension of the annihilator. Suppose V is finite dimensional and U is a subspace of V. Then the dimension of U plus the dimension of the annihilator of U is equal to the dimension of V. We also have some theorems about the null space of the dual map. Suppose V and W are finite dimensional and T is in the space of linear maps from V to W. Then the null of the dual map of T is equal to the annihilator of the range of T. Second, the dimension of the null of the dual map of T is equal to the dimension of the null of T plus dimension of W minus dimension of V. And then finally, we have these last two theorems. T is surjective is equivalent to the dual map being injective, and this theorem, T is injective, is equivalent to the dual map being surjective. Our very last topic is the matrix representing the dual map of T, and that will be equal to the transpose of the matrix representing the linear map of T. And here's the statement again: the matrix of the dual map of T is equal to the transpose of the matrix of T. The definition of the transpose of a matrix A, denoted with A superscript T, is the matrix obtained from A by interchanging the rows and columns. So for example, here we have a matrix A with column vectors 5, 3, -4, -7, 8, 2. So we'll take this first column and transform it into the row. So we have 5, 3, -4. We'll take the second column, transform it into the second row, -7, 8, 2. We also want to keep in mind the transpose of a product of matrices, that is, A times C transpose is equal to C transpose A transpose. So our full theorem here for the matrix of the dual map of T is the transpose of the matrix T. Suppose T is an element of our linear maps from V to W, then the matrix representing the dual map, or T prime, is equal to the matrix of T transposed. To review what we have covered in this video, we have looked at the dual space and the dual map. We started by defining a linear functional. So a linear functional on V is a linear map from V to F. It is an element of the set of functions, linear functions, from V to F. So examples included the functional going from the polynomial space to R, which is defined by 3, the second derivative of our polynomial evaluated at 5 plus 7 times the polynomial evaluated at 4. We can see that it is a function from the space of polynomials because we take our polynomial here, P, and it maps to a real number. Once we evaluate the second derivative and the function at a particular point, we'll start getting real numbers. Our second example was another linear functional from the space of polynomials to R, and this was an integral example. So we take our polynomial P and we make it into, or map it into, a real number by taking the integral and then evaluating at 1 and 0. We define the dual space of a vector space V, and we denoted that with this V prime. So that's the vector space of all linear functionals on V. So that is the dual space of V is equal to the set of linear functionals from V to F. Our two examples above over here, the one involving the derivatives and also the one involving the integrals, are vectors in the dual space of P, the polynomial space over R. We have the following theorem. If V is finite dimensional, then the dimension of the dual space equals the dimension of V, and the result is that V and its dual space are isomorphic. We define the dual basis, so once we have our vector space and a basis for our vector space consisting of the vectors v1, v2 up to vn, we can then define a dual basis of v1, v2 up to vn, and that will be the list v1, v2 up to vn, where each phi sub j is the linear functional on V, such that phi sub j operating on the kth basis vector of V is equal to 1 if k equals j, and 0 if k does not equal to j. And in effect, what this does is this dual basis will pick out the jth coordinate of any vector in our vector space V. And we have this theorem here. This dual basis that we just defined above is a basis of the dual space. Next, we define the dual map. If T is an element of the linear maps from V to W, then the dual map of T is the linear map denoted with T prime in the space of linear maps from W prime, V prime. We define that dual map T prime of phi to be equal to phi composed with T. We covered these algebraic properties, which I'll let you read over. And then we also talked about the annihilator. We defined the annihilator for a subset U of V, and we denote that with this U superscript 0 is defined to be the phi in the dual space such that phi of U, the vector U, is equal to 0 for all vectors U in the subspace U. We had other theorems regarding the annihilator, as well as relationships between the null space of the dual space and V and W. And finally, we said the matrix of the dual map is equal to the transpose of the matrix representing the original transform T. And that's it for this video. Thank you for watching.